Hello. So, in the last phase of these lectures, we are going to discuss some approximation algorithms. So, let me start with some basics. You must be familiar with some problems are known to be NP hard. In another set of lectures, you may have seen NP completeness and examples of those. So far, we do not know whether the class P and NP are equal, but if we assume that they are not equal, then we do not hope to be able to solve those problems in a polynomial time. Now, in that case, what we would like to do is try to approximately solve those problems. So, first of all, let us try to precisely describe what do we mean by approximate solutions. So, in this context, the approximation algorithms refer to a class of problems, namely optimization problems. Not all problems are in this category, but often what we tend to do is we transform any problem into an optimization problem and then try to solve those approximately. So, let us suppose we have an optimization problem in which we are given some background and we are given some optimization function, some function of few parameters, and our objective is to minimize or maximize this, to find an assignment to various parameters which optimizes this function. We know that to compute the most optimum value of that function is hard. In that case, what we would like to do is, okay, if we can't determine the optimum value, let us find some good value. And we say, all right, how good is it? For that, we can actually take the ratio of the two and say, all right, suppose this was a maximization problem. We do not reach as far as this. So, this is actually less than 1. We know that it is less than 1. But can we say that it is definitely not smaller than some value alpha? If we can bound this ratio, we guarantee that no matter which instance of the problem you give me, I will give you a solution where the object function will not be too far from the optimal value, that is to say the ratio of the two will be bounded by alpha. In case of minimization, similarly we will have a bound on the other side. Now, this alpha could be a constant or even a function of the parameters. Some cases we cannot do too well, then we have some function of parameters. For example, if we can give a say 1/2, 3/4, 1/3, that kind of bound, that is fine. But if we can't, then maybe we can say, all right, 1 over log n or n to the power -2 or -0.2, that kind of bound would also be fine. It depends on how well we can approximate that problem, because sometimes even approximating in a sense, in this sense, with binding the ratio by a good number is also very hard in many problems. So, this parameter is what we are after, and this is known as a performance ratio. In our case, we will keep this. Sometimes people normalize this for maximization and minimization, but in our case we will just stay with this interpretation of performance ratio. So, if this is the goal, to push this to 1, one of the key element in the design of the algorithms is to be able to analyze it. Although we do not know this value, we need to show that this is very close to this without actually having this with us. So, one of the ways to do that is to find some quantity which is not necessarily quite relevant to this problem, to determine some value for which we can say, let us say that value is q, and we can say that that value is greater than equal to q opt. So, I am talking about my reference is maximization. So, obviously, this is not the value of phi for any instance of the problem, that is not possible. So, it is probably some other quantity. And then to relate this q with q phi good, the value that we compute through the approximation algorithm, and that way we can actually find a bound. Today I am going to discuss two examples of two very simple examples that will give you some flavor of the way one analyzes. Usually these algorithms are not that difficult. Well, at least these elementary cases that we will discuss, the algorithms will be simple. It will be the analysis which will be somewhat less simple. Now, let me also now describe something called PTAS. Unlike optimization algorithm, this is known as a polynomial time approximation scheme. Here what we are trying to do is, given an epsilon, once again let us assume we are talking about maximization. Given an epsilon, if we can provide within this scheme a method such that my phi good over phi optimal is greater than equal to 1 minus epsilon. In other words, I can bring phi good arbitrarily close to phi optimal. But then you might wonder, well, how can that be? We have to always provide a polynomial time solution, always. There is no discussion of because there is no point in approximating as well as spending time, huge amount of time in solving it. So, there is a polynomial time algorithm and we are bringing it arbitrarily close to the optimal, but there must be some catch. So, the answer is that as we bring epsilon close to 0, the cost grows. So, it may happen that the time complexity might be function of 1 over epsilon. So, the time complexity of this may be quite reasonable when epsilon is large, but as we bring it closer to 0, this blows up. So, this can be very bad. Now, in general it could even be like say an exponent on some parameter. That may well happen, that the complexity is a function of this form. In case the time complexity is not of this form, although it is a function of 1 over epsilon, but maybe some polynomial of this, maybe something power k occurs in the time complexity, which is not so bad as this one. If we can guarantee that my time complexity for this is partly a polynomial of this, then we call it a fully p-TAS, fully polynomial time approximation scheme, or FP-TAS. We will have one example of this as well in the following lectures. So, let us start with a first example, that is something called vertex cover. Let us describe the problem first. So, problem is that let G be a graph and we want to compute smallest possible vertex cover of G. So, what is vertex cover? So, the vertex cover of G is a subset of V. It is a subset of vertices such that every edge in E is incident on at least one vertex of this set. So, let us suppose we have a graph then perhaps so if I try to cover these three, that will take care of well, it does not matter, it is not terribly, I can avoid this. So, I am taking these vertices in the set. Now, what we notice is that every edge there are two vertices incident on an edge, at least one of those two vertices of every edge is in this set. So, this edge has this vertex in the set. Similarly, these two edges also have some vertex in this, and so on. These are obviously both the end vertices of this edge are inside the set, and so on. So, if I label them 1, 2, 3, 4, 5, 6, 7, 8 and 9, then one possible vertex cover is 2, 3, a vertex cover is 2, 3, 5, 8 and 9. Okay. So, this is a possible vertex cover. The size of this vertex cover is 5. There are 5 vertices in it. So, the challenge is to compute the smallest possible vertex cover, that is, say, vertex cover with the minimum cardinality. That is what we would like to compute. This is known to be an NP-hard problem. So, the optimum vertex cover, this is naturally an optimization problem. Okay. There are problems which are not naturally optimization problems, and one sometimes artificially converts them into an optimization problem, but this one is an optimization problem. So, the smallest vertex cover is not always possible to compute in polynomial time. So, our problem is actually a minimization problem. Our goal is to compute a vertex cover. Our object function is the cardinality, a vertex cover C, cardinality of C, such that C divided by C opt is as small as possible. We would like to bound this value above. So, usually the I would say the cardinality of this. So, we would like, usually this will be bigger than this, we would like to bound it by upwards. So, here is a very simple algorithm. First, pick an edge from E. Say edges, say U comma V. Okay. Put it in a set A. So, I am just picking an arbitrary edge and putting it into a set A. In step 2, remove every edge in E of the form U something or V something. So, I take this edge, put in a set, and every edge. So, here is the picture. I had picked up UV, and if there are edges here, so I am going to remove them, put this into set A, and then iterate, okay, and then keep doing this until edge set is empty. Okay. So, to be more accurate, let us just write down. Okay. we have, let us say f is E, we initialize a set A to be empty, and then while f is not empty, repeat these steps, okay. Select uv from f. F is initially the whole of E. We select this, okay, delete every edge from F which is incident on U or V. So, this is where the while loop ends. Now, I have to produce a vertex cover. So, my cover C would be all the vertices such that this edge is in F, in A. So, you just pick all the end vertices of edges in, yeah. Oh yeah, I have select A and put in A U comma V, sorry. So, I am going to take this edge, put in A, remove everything else of this form, these edges. After you are through with this process, you pick up the end vertices of the edges stored in A. All right. So, there are two things I have to show. Okay. First, one, that C is a vertex cover, and two, that is bounded by some alpha, which we have to decide whatever this alpha is. Okay. So, let us just look at the first objective. What we have computed, so observe that A is a matching. Now, just to remind you, matching is a subset of edges. Remember, A is a collection of edges here. So, matching is a collection of edges such that no two edges share any vertex. What we are doing is we picked this U1, V1 and we removed all the other edges. After that, in the second round, when I am going to pick an edge, I am going to pick an edge between completely different pair of vertices and so on. So, every edge that I pick, so there are other edges and all that. Everything that I pick will be between completely fresh pair of vertices. Such a thing is a matching. Well, in that case, my claim is that C opt cardinality cannot be less than cardinality of A. You cannot have any vertex cover with cardinality less than the cardinality of A. The reason is simple. Any vertex cover must pick at least one of these two vertices. It cannot avoid both, otherwise this edge will never be covered. Similarly, it must pick one of these two and one of these two. So, from every one of these matching edge, one of the two end vertices will be put in any vertex cover, in particular C opt. Hence, the size of A is a lower bound for the optimum vertex cover. Now, why does this pair, what we have put in C, the cover that we have computed contains both of these vertices? Why does it form a vertex cover? And the answer is simple, that suppose there is an edge which is not incident upon any of these vertices. Such an edge will remain in F, it will not be deleted, because all you delete is only the edges incident upon the end vertices of the picked edge. F will not go empty. So, if this was eliminated, if this was not covered here, either this is covered as a member of A, no problem then, else this fellow must have been eliminated. If this was eliminated, then certainly this might be an edge of this kind somewhere. Hence, we know that this vertex is in C. So, that takes care of the fact that C is indeed a vertex cover. And now, what about putting a bound on the ratio or computing the performance of this approximation? And the answer is, an obvious claim is that the size of C is equal to 2 times the size of A, because all we do for every edge in A, we put these 2 vertices in C. So, we have this. Hence, C over C opt, the cardinality of these 2. So, this is 2A and this is greater than A. So, this is greater than or equal to 2 mod of A divided A, which is 2. Since this was actually smaller, so here it is greater. So, we have an upper bound for this ratio as 2. So, we can never do much worse than twice. It does not matter how we select the edges from F. So, this is a very simple example how easily I can perform this task of computing a cover which is no more than twice the optimum. While optimum takes enormous amount of time, this is a very simple polynomial time algorithm. Okay, so now let us look at a second example. The second one is about traveling salesman problem. With so, let us first of all describe the problem. You must be familiar with a well known NP hard problem known as Hamiltonian cycle problem. So, in Hamiltonian cycle problem, you are given a graph G and you would like to know if there exists a cycle. Okay, there are certain edges we would like to know if there exists a cycle. A cycle is a closed walk in which we do not repeat any vertex. So, probably all right. So, maybe very hard to see, but the objective is to find a cycle which passes through all the vertices. Okay. And this is also a well known hard problem. No polynomial time algorithm is known. A variant of this problem, which is an optimization, this is not an optimization problem. Either you have a cycle which passes through all the vertices or you do not. But a traveling salesman problem is a variant of this problem, which is of the optimization flavor. And in TSP, which stands for traveling salesman problem, we have the following statement of the problem. So, we are given G with edge weights. And G is a complete graph. A complete graph is one in which there is an edge between every pair of vertices. It is also known as Kn. G is a Kn, complete graph on n vertices. Edges have weights. Now, in a complete graph, to find a cycle passing through every vertex is a trivial task, because every permutation of vertices is a cycle in a complete graph, because all pairs are connected. So, the hard part is not to find a cycle, but to find a cycle whose weight is minimum. So, the cycle weight in this case is the weights of the edges of that cycle. If I have this cycle, let us say these are the only vertices of the graph, there are other edges, of course, we are not concerned. There are edges between every pair, of course, but the weights that we are interested in are, so this is the cycle. W1, W2, W3. We would like to minimize the sum of these weights. These are the weights of the edges on the cycle. Now, one can show that this has to be NP hard. The reason is we can solve the Hamiltonian cycle problem if we can optimally solve the traveling salesman problem. The reason being, you give me arbitrary graph G. So, I have this some graph which is not complete, of course. I can put weight of 1 unit on these. And then I add edges which are not present. I put all the edges and put infinite weight on those, infinite weight. Now, this is an instance of TSP. Find the optimum solution of this TSP. If there is a Hamiltonian cycle, we know that there exists a cycle with weight n, because there are n vertices on it, n edges on this cycle, each has unit weight. So, there will be a solution with weight n, otherwise weight will be infinite. So, immediately it can tell whether this is whether this has got a Hamiltonian cycle or not. So, indeed exact solution is hard, but we are going to make one more assumption about this. What we assume is that the weights are such that they satisfy a triangular inequality. What it says is that suppose you have in this graph G, which is Kn, whenever you have a triangle, if the weight of this edge is W1, this is W2 and this is W3, in that case W3 is always less than equal to W1 plus W2. Well, by the same token, W1 is less than equal to W2 plus W3, or W2 is less than equal to W1 plus W3. When this condition is satisfied, we can give a decent approximation algorithm. So, let us now consider the following algorithm. Notice that this is again a problem of minimization. You want to compute a cycle, Hamiltonian cycle in this graph with minimum weight. So, the step 1, instead of formally writing it, I will actually describe by diagram. First one is to compute a minimum spanning tree. T. Okay, so here we have graph G, which is of course Kn, and a weight function W in G. So, we begin with a spanning tree, a computation of the minimum weight spanning tree in G. Notice that there exists an algorithm to compute minimum spanning tree in polynomial time. Okay, so let us suppose we have some tree, but I am drawing this tree with a particular objective. I am picking any one vertex and calling that as a root. So, we actually draw the tree in that fashion where the root comes and then it just falls down. Now, we are going to compute a pre-order traversal of this. So, pre-order traversal is in the following fashion. We start with the root, then we do the pre-order traversal of this subtree, then pre-order traversal of this tree, subtree, and then of this. So, pre-order traversal is defined recursively. Let us actually go through that. We come here, then we come here, then we go to this guy, then this, because these are the three subtrees of this. Then we come to this, and to this, and then to this, and this. So, let us now label them the order in which we visited: first, then second, third, fourth, fifth, sixth, maybe I will just, for the sake of an example, 7th, 8th, 9th, 10th, 11th, 12th, 13th, and 14th. This is the order in which we will traverse. This particular order is my output. So, output, so step 2 is output a pre-order traversal of T. We know that any permutation of the vertices forms a Hamiltonian cycle in a complete graph Kn. So, this indeed is a valid, because there are edges between every pair. So, how good are we doing in terms of the performance compared to the optimum? Okay. So, let us do the following. First thing we are going to do is generate this traversal . what we are doing is we are writing a closed walk 1 to 2 to 3, back to 2 to 4, back to 2 to 5, back to 2, back to 1, then 6, 7, 6, 8, 6, 1 and so on. So, you visualize this picture. Let us call this closed walk, I am going to call this closed walk or label it by S. Now, I am trying to determine how good is this output. So, what we have done is we have basically covered this tree by a closed walk and we are calling it S. Then what is the weight of S? Note that weight of S is the sum total of the weights of its edges. And what we are doing here is we are, you look at any edge, we are once going in one direction and second time we are going in the other direction in every single one of these. So, the weight of this is precisely 2 times the weight of the tree, which is trivial. Okay. Now, neither of these two are of any interest to us. This is not output and this is not even a cycle. It is not a cycle because we are revisiting certain vertices. Now, what we will do is the following. Let us look at this 3, 2 and back to 4. What we will say, let us cut this off and connect this directly. So, we have taken this off 3, 2, 2, 4 and replaced that by 3, 4. And triangular inequality says that the weight cannot increase. Once we do this, the weight cannot increase. By the same token, we will directly go from 4 to 5 we will directly go from 5 to 6. Now, in this case, let us just see carefully. Actually, I have replaced 5 2 2 1 by 5 1 first, and then 5 1 1 6 by directly 5 6. In other words, in every step I have used the triangular inequality to argue that the resulting cycle as we go on cannot weigh more than the weight of S. At the end of the day, the cycle that we will be building is nothing but the cycle we have. So, let us call this cycle C. So, the triangular inequality ensures that due to the triangular inequality, the weight of C is less than equal to the weight of S. Okay. So, we now have at least an upper bound for the weight of the C, but still we have to somehow bind this above by the weight of the optimum traveling salesman problem solution. All right, but that is also very easy. Let us suppose C opt is the optimum cycle, optimum TSP solution. All right. Take this. So, this is some cycle which I cannot draw on this. I am just for the sake of visualizing, I am just thinking, let us say this is that C opt passing through every vertex. Pick any edge E and just delete it. So, what you get is that the weight of this is this path P. So, the weight of this P is actually equal to the weight of C opt minus weight of E. Now, temporarily let us assume weights of all the edges are non-negative. We will take care of that general case in a minute. Assume this. In that case, this is actually a tree, path is a tree. So, we know that the weight of P has to be greater than equal to weight of T, because this is a spanning tree, because it passes through every vertex, and T is one of the optimum spanning trees. So, this argument simply shows that the weight of C opt is greater than equal to weight of P, which is greater than equal to weight of T, the optimum spanning tree. We are done. All we have to do is put the whole thing together. So, let's do that. The whole thing now comes out to be WC, the weight of the cycle computed, is less than equal to WS, which is less than equal to 2 of WT, which is less than equal to W opt, so which is 2 W C opt. Hence, WC divided by WC opt is less than equal to 2. Once again, we have a performance ratio of 2. Now, to wrap this finally up, one more question I have to solve. What happens? What happens when there are negative weights? Some edges have negative weights. Well, so suppose I have my graph. Let us say the weight is okay. So, this is minus 2, 5, 7, minus 3, 4, 8, 6. Well, the smallest number is minus 3, we will add 3 to everybody. Let us put plus 3. Okay. Well, indeed, this is a new set of weights, and there are no negative weights in this. But how is it related to the old problem? So, the answer is very straightforward. Everybody has added 3 weights, and in any Hamiltonian cycle, any cycle passing through all the vertices, there are exactly n being the number of vertices, there are n edges. So, if the weight of original cycle, let us say C original, is always C new minus 3n. The 3 new, in the new we are adding 3 units per edge uniformly. So, this is a constant. So, whatever be this value, n is a constant, and this is the weight of the smallest cycle, the smallest weight edge. Hence, to solve the problem on the original graph or on this graph is same. It is just you have to minimize this, or you minimize this, or you just minimize this. It is the same thing because this is just a constant. Hence, it is sufficient to assume all the weights are non-negative, because the moment you have negative weights, simply upgrade the weights by a constant, so that there is no negative weight. Okay. So, here is we have given two examples of approximation. Incidentally, both of them had constant performance ratio. We will see some other examples in the following two lectures. Okay.